Okay, then let's start. It's a great pleasure to have, for the first time, 3 speakers in the distinguished lecture series of CASA. We have Asokan, Buse, Atli, and Sebastian Szyller. And today, the 3 of them will be talking about deep learning systems, especially about extraction attacks. And we are very looking forward to get the answer whether they are a real threat or boogeyman. Yeah, let me shortly introduce our speakers. I know Asokan for, I think, over 10 years now. We met for the first time at CCS in Chicago in 2010, when I was just beginning my PhD. And at that time, he was working for Nokia, and he was leading the security lab there. And then he moved to academia. He became professor at Aalto University in Helsinki in Finland. And since 1 year, I think, he's professor at University of Waterloo for computer science, and he also holds a David Cheriton Chair. And he is still adjunct professor for computer science at Aalto University. So Asokan has a background in industry research and academic research, and his research is widely visible. For instance, he received the ZigZag Outstanding Innovation Award for his contributions, especially in trusted device pairing. I think that's something he did when he was at Nokia, and also trusted execution environments for mobile systems. But today, he will be more focusing on the machine learning part, which is, of course, a very crucial aspect also of CASA, where we are looking into different algorithms and their security. Asokan is a very good supervisor, I can tell you that, even that I was not his PhD student, but over the years he gave me so many good advices, especially during my PhD time, which were very valuable. And this is also confirmed by the fact that he invites his students to join his distinguished lecture and also have the opportunity to reach a broad audience. And today we have Buse Atli. She did her master's in signal and speech and language processing at Aalto University. She also interned at Nokia Bell Labs, and her research focus is on security and privacy of machine learning. And we also have Sebastian Szyller, who did a master degree in machine learning and data mining at Aalto University, and also has some industry background. So all of our speakers have industry background. He worked as a software engineer in an investment banking company. So with that, I hand over to Asokan, and we are very looking forward to your talk. And thank you for giving this talk.
Thank you, Luca. So Luca said I was advising him informally. Now, once in a while, a student comes along who is such a good advisee that even if you're not a formal advisor, you feel drawn to mentor and advise them. So Lucas was such a student, and I appreciate not only interacting with him sort of informally as an advisor, but also collaborating. So I think we had a couple of papers, which are very interesting papers. Yeah, so like he said, this is going to be an unusual talk in the sense that there's going to be 3 of us. And the reason for this is that professors like me get invited to give talks, and this is very rewarding. You go somewhere, meet with colleagues and students, give a talk, and during normal times, it's not realistic to take students along, right? So if the people who invite you would be reluctant to pay for like an entourage of students. So this pandemic has been really bad in many ways, but one of the few good things is that most of these events are online, and therefore it allows me to take an opportunity like this and also expose the students who did the actual work to be part of a keynote like this. So I would encourage those of you who are professors to do the same, give the chance for your students to talk to a broad audience, and it'll give them the credit that's due, but also it's a good learning experience for them. So with that, we like Luca said, we have I have two students with me. Buse, say hi. Buse is a senior PhD student who has been working on this topic and also other related machine learning security topics. And Seb, say hi.
Hello.
Seb is also a senior PhD student who's been working on security and privacy of machine learning. And so we are both going to talk about our work on model extraction. So the structure is going to be that I'll briefly try to convince you that model extraction or model confidentiality is important, and therefore model extraction is a concern. And I'll spend the bulk of the time talking about whether models can be extracted, and I'll explain what we mean by extraction. But for now, you can think of this as sort of stealing the model, whether models can be stolen via prediction APIs, and then depending on the time, might also delve into a little bit into what can be done to counter model extraction. So let's start with whether model confidentiality is important. So machine learning models, all of us know that machine learning-based systems and machine learning as a technology is really coming in like a train, right? It's taking over all aspects of human endeavor, right? Every profession is being impacted by that, and it's because it has had some good results, and people see the potential, and therefore it's transforming, not just security and privacy, but also other computing applications and even other aspects like jurisprudence and human resources, recruitment, and so on. And the attraction is that this machine learning, the trouble that people go to build, design and build a machine learning model constitutes a business advantage, right? So they can make money out of that. In a way, it's like intellectual property. But this comes with certain costs, right? So the primary cost would be that training machine learning models require usually lots of data, especially deep learning, which is quite successful recently. And in particular, if the data has to be labeled, right? The data has to serve as ground truth, then labeling is a resource-intensive and time-consuming process, and that can cost a lot of money. Once you have the data, you have to choose the right model and the right training method, and this is as much an art today as it's a science. So again, it requires expertise, which means money. Then finally, the actual computational resources that are spent in training, involving like tens of thousands of hours of compute time and memory and so on. So if an adversary can sidestep all of these, but still get the benefit of a model, then that incentivizes them to try to steal the model. And like any technology which is successful, bad people will be attracted to that. So people with adversarial mindset will be attracted to that. And one of the adversarial intents would be to steal a good model so that the adversary can undercut the business of the model owner by providing the same kind of prediction service at a lower price and so on. So what kind of, what do we mean by model theft? So the simplest type of access one can think of is like white box access. So this is when I try to train a model and maybe I sell it to my customers or I rent it to my customers, sort of like the software business model, right? Shrink wrap software kind of business model. So this means that the model, which is the item of value, is physically given to my customers. And so the user, the customer, one of whom might be adversarial, has physical access to the model and therefore can know its structure and can observe its execution and so on. So there have been a number of mechanisms that have been proposed to deal with this kind of adversary who has white box access to the model abusing that access, right? So people have proposed using cryptographic techniques like homomorphic encryption. So you can encrypt a model and the customers only get these encrypted models. They can still run their data through the model and get predictions without actually knowing what is inside the model. So this may be one way. Another way might be to rely on hardware security mechanism, right? So I'm sure all of you know that every smartphone that's out there and many other computing platforms have some kind of hardware security mechanism, like trusted execution environments, and that can be used to protect some code that's running on the device, expose an interface that other applications or the user can use without actually getting hold of the model itself. Or you can put the model behind a cloud service and then have a sort of firewalled access to the service via some kind of an API. So all of this have this common property that they turn this white box access into a black box access so that customers don't have direct physical access. They can only interact with the model via a well-defined interface. Perhaps it's a direct prediction API, such as in sort of translation models or image classification model, where you give some input and get some get the output of the model on that input returned back to you. Or it can be done indirectly, like there may be a machine learning model that's computing recommendations, where what you would see is based on your behavior, you would see some recommendations. But nevertheless, the customers of the model are interacting via a well-defined interface. So once you do that, once you hide the model and make access to the model via prediction API, it's natural to ask, does this address this model stealing problem? Is this enough to prevent model theft? And when you know that whenever there's a rhetorical question like this, the answer is likely to be no. And this is what I'm hoping to try to convince you in the rest of this talk. So prediction API, so there's some victim model that is behind the prediction API. And like you said, the client is only allowed to interact with the model via the prediction API. So the prediction API is essentially, you can think of it like an oracle. Each time you ask a question and gives you an answer, it necessarily leaks some information. So it's not surprising that in a given unlimited set of questions, a client will be able to receive enough information to build a model that's functionally equivalent to the victim. But as it turns out, you don't really need in this kind of unlimited or intractable number of queries. You can reproduce the functionality of a victim model by using this API to make a reasonable number of queries and build a surrogate model. And the surrogate model, depending on the adversary's goal, for example, would have equivalent functionality by some metric compared to the victim model. So this is the problem of model extraction. And when my students started looking into this like 3 years ago, there were already some prior work that showed that model extraction via the prediction API is possible for fairly simple models like logistic regression or simple convolutional neural networks. And the basic sort of approach was you take the API and you generate a number of sort of synthetic queries, not real data, but data that's designed to explore the model and get enough information so that the adversary can train the surrogate model. So our first work in this area, which was published last year, where we showed that it's possible to extract deep neural networks with fairly reasonable, but still sort of relatively simple data sets and problem domains. So MNIST is handwritten digits, there's a data set with handwritten digits that machine learning people typically use to demonstrate ideas. GTSRB is a German traffic sign data set where there are a collection of traffic signs, and the model that you build should be capable of distinguishing between traffic signs. So our adversary model was that the adversary knows the general structure of the model, but doesn't actually know the model details, but also that the adversary has some limited set of natural data drawn from the victim domain. So for example, in the case of MNIST, which has 10 classes, the digits 0 to 9, we assume that the adversary has some examples of each of these classes, but not enough to train its own model. Similarly, in the German traffic sign, there are, I don't remember, some 20, 30 odd classes, and we assume that the adversary has some examples of these. And the basic idea was that the adversary would sort of do an initial search for determining the hyperparameters of the model, but then start with this limited natural data as kind of starting points of the initial classes, but then use synthetic data to fine-tune the search to explore the class boundaries. So in this paper, we showed that it is possible to extract these models. We also devised a simple defense mechanism that essentially relied on distinguishing between benign and adversarial queries. So remember that we said we made some assumptions about what the adversary has access to, and also previous work did the same. And one of the assumptions was that the adversary doesn't have access to a lot of natural data from the same domain. So somebody who's using German traffic signs doesn't have a lot of pictures of traffic signs. They have some, but not enough to train their own model. So therefore, this defense sort of rests on this fact that the adversary is forced to use a lot of synthetic query, which will look statistically different from natural queries that legitimate customers are going to use. And the defense sort of relied on this being able to tell the difference between these two. So when we presented this to program committees, but more importantly to sort of our industry partners, the questions have always been that, okay, you have shown that it's possible to steal simple models like handwritten digits and traffic signs, but is it the case that these models, more complex and more realistic model, can also be stolen? Another question was, we made some assumptions about the adversary capabilities. Are these realistic? And like I said, the adversary model that we assumed was in line with the adversary model that was assumed by prior work. And then the last question is, of course, I think it's useful to show that a threat is realistic, but what about defenses? And the kind of defenses that we and others have done, are they effective? So we, Luca told you earlier that we have been working together in previous contexts, and one of the contexts was an Intel Collaborative Research Institute that we and Darmstadt, where Luca used to be, were part of. So this is one of the questions that the Intel experts ask: is can you steal realistic models, and can you find effective defenses? So a year and a half ago, or maybe a little under 2 years ago, we started looking into this, and we noticed that there was a paper from folks at Saarbrücken called Knockoff Nets, which was a follow-up of our work, but at that time, this was sort of the state of the art in model extraction. So we wanted to systematically look at knockoff nets to try to answer these questions. And knockoff nets had their approach was the same. They wanted to build a surrogate model that steals the functionality of the victim model and essentially performs the same task, in this case, the classification, image classification task, with high accuracy. They made some interesting assumptions about the adversary models, and some of them were more realistic and assumed less from the adversary than we did, and some of them were more. So I'll sort of list through them, and then in our work, we tried to systematically look at different types of adversary models and how knockoff nets would function with respect to those models. So unlike us, they assume that the adversary doesn't know anything about the model, possibly doesn't even know what the model is for, doesn't have access to any data with respect to what the model is doing. But they did assume that the model would return a full prediction probability vector. So in the case of classification, it's not just going to tell you, given an input, which class it belongs, but it's going to give you a probability vector that says, for each class, this is the likely probability that this input image belongs to that class. They did assume that the adversary has access to natural samples, but not from the same distribution as what the victim model was. So In the case of attacking handwritten digits, they didn't assume that the attacker had other handwritten digits, but they assumed that the attacker had some images, something that falls into the domain of images, but not necessarily handwritten image, because remember that the attacker doesn't even know what the model is intended to do. They also assumed, and this is something that we had started to think about earlier, that the attacker and the victim were deriving their models from pre-trained high-capacity models. So the victim didn't start training a model from scratch. And similarly, the attacker knows potentially which model the victim would have started from, and therefore could start from the same model. And this is a reasonable assumption because this practice is very common, that people have, like if you're doing anything with images, you would pick a model that is trained on ImageNet, which is like a dataset with general purpose images. But then the designer would then fine tune that model for the particular task that they are interested in, and recognizing handwritten digits or recognizing X-rays with diagnosis or whatever. So this is common practice, and therefore it was reasonable to assume. And our intuition when we started this, and the same intuition that was held by the knockoff people, is that by making these realistic assumptions, you could now steal more real-world models than was possible before. So at this point, I will hand over to Buse to describe what we did with knockoff nets. And essentially what we wanted to do was first reproduce their work to make sure that the claims that they were making are correct. And then second, we revisit the assumptions, like in terms of adversary model, in terms of assumptions about whether whether the victim built their model from a pre-trained model and so on. And this is as a way to sort of shed light on the questions that we started out with. So I will then let Buse describe the next few slides, talking about our work on knockoff nets and reproducing them and analyzing them. Buse.
Thank you. Yeah, as Asokan already said, our goals in this work is first reproduce the empirical evaluation of knockoff nets in different experimental setups with different victim models to confirm its effectiveness. And second, we introduce a defense mechanism within the adversary model, Asokan just explained, to detect attackers' queries. And then finally, we revisit the adversary model in different conditions. Next slide. With different conditions, I mean, with different adversary models that could be more realistic. And we explore the impact of these different adversary models on both attack and defense effectiveness. I will explain those in detail, but basically, we showed that attack effectiveness decreases when you have an architecture mismatch between surrogate and victim models, when you have a reduced granularity of victim predictions API's output, or if you have a reduced diversity of adversarial queries. We also showed that the defense effectiveness also decreases when the attacker has natural samples, has queries distributed like victims' training data. It's more close to the victims' training data. Next slide. First, I will talk about the experimental setup we have, and also in the original paper in knockoff nets. As Asokan said, we assume that victim models are derived from public pre-trained high-capacity models, and we use ResNet34 model, which was trained on ImageNet database. It's quite a good assumption because usually many prediction aid commercial APIs like Microsoft or Google uses this kind of public pre-trained model, so it's perfectly fine assumption. And the attacker strategy is to first collect unlabeled natural data. Attacker can collect this natural data from big databases like ImageNet, Open Images, or just by using Google. In this work, we were focusing on this image classification. So attacker collects images as a natural data, and it may not be out of target trained test distribution. Attacker doesn't care about how close they are in the victim model's training data set. And after collecting this natural data, attacker queries the API to collect victim outputs. Victim outputs are probability vector for each query, and we use approximately 100,000 queries to generate this probability vector and also the transfer set of the attacker model. And then the attacker constructs the surrogate model. Next slide. Again, since the attacker can also assume that the victims are derived from public model, attacker selects a pre-trained model and fine-tune it with the transfer set he constructed. And with this Tesla V100 GPU, we measured that it takes 3 days to train a surrogate model. And since for per query you pay some price, the estimated cost is between $120 to $170. So first like I said before, we try to reproduce the experiments in the original paper, and for that we use 3 different models with 3 different data sets: Caltech, CAPS, and diabetic. They are all trained with ResNet-34 models. Also, the surrogate models are you train with ResNet-34 pre-trained models. So Caltech data set is kind of general image classification data set. It includes more than 200 classes. CAPS is a bird classification data set. Again, it includes 200 bird classes. Diabetic includes like 5 classes, and it is composed of diabetic retinopathy images, and it detects the severity of the diabetic retinopathy illness. GTSRB is German traffic sign classification data set, and CIFAR-10 is again used for general image classification, and it includes 10 classes. So this GTSRB and CIFAR-10, these were not in the original paper, but we also try to reproduce the performance of the knockoff nets. As you can see in the top two, our reproduction results are quite close to what was reported in the original model. But for the diabetic 5, we have a little bit different results due to the difference in our victim model and the victim model reported in the original paper. What we did is we augmented the data set to get a better victim model. Since you have different victim models, you have different model outputs, probability vectors, and then you have different surrogate models. And for the top 2 rows, we have again good performance recovery of knockoff nets. So we can say that knockoff nets are definitely effective against complex pre-trained DNN models. Yeah. Next slide. So like I said before, we revisit the adversary model a couple of times and see what will happen to the effectiveness of the knockoff attack. The first one, we asked the question of what if we reduce the granularity of the prediction API's output. As you can see in this slide, Google Cloud Vision, Clarify, or IBM Watson, these are quite popular commercial APIs. But if you use their general prediction API, they only give top 10, top 20 results, although they include more than maybe 100,000 image classes or labels for one image. So that's why we try to reproduce the results when the victim prediction API only give one label, the top label. Remember that the original adversary model expects a complete prediction vector for each query. Now you have just one label, top label. If you have more than 200 classes, the effectiveness degrades when the prediction API gives only the top label. But if you have a less number of classes in your victim model, especially if you check this diabetic model, the effectiveness does not degrade at all. So effectiveness degrades with respect to the number of classes in your victim model. Yeah. Next slide. We also revisit the adversary model when you have an architecture mismatch in surrogate and victim models. Again, in adversary model, in the original paper, we assume that victim model uses pre-trained DNNs, publicly available DNNs. And first we try to change if the pre-trained DNN used in the surrogate model. So we have two different experiments when you have the surrogate model as ResNet34 and VGG16. It's also a pre-trained DNN. And we tested on GTSRB and Cypher10 victim models. As you can see, there's a little bit decrease in effectiveness, but not much. You still have a fairly good surrogate model. But if you, as a victim model, if you have a completely different architecture, in the bottom two row, you have like 5-layer GTSRB and 9-layer Cypher10. These are not pre-trained DNNs. These are specifically designed for that data set. When you have the surrogate model, pre-trained DNNs, then the effectiveness degrades a lot. So the effectiveness degrades when the victim is not based on pre-trained DNNs. Yeah, finally, we know in this case, we won't revisit the adversary model, but we want to explain the limitation of the knockoff nets due to the adversary model itself. So in the previous slides, we always check the test accuracy, average test accuracy. But if you check the per class performance, per class test accuracy, the knockoff nets cannot recover this per class performance of the victim model much, because the aim of the knockoff nets is only to reproduce the average test accuracy to get as high as test accuracy as in the victim model. So knockoff nets doesn't care about recovering decision boundaries of the original victim model. So for that, we plot we have this TSNE plot of victim and surrogate model. And as you can see, victim model on the Cypher10 data set, it has a good clusters. You have like cluster for every classes, but for the surrogate model, it's a little bit overlapped. And for example, in the horse classes, you have a good cluster on victim model, but you completely lose the horse class in the surrogate model. And when you check the test accuracy on the horse class, it's really lower than the victim model. And also when you check the histogram, you have a really less number of samples for the horse model. Again, for example, cat model, you have a good test accuracy for the cat model, good big cluster for the cat model. Again, you have a good big number of samples for the cat class. So this can be, this limitation may not be important if you have like a general classification API, but if the victim model's prediction API is used for medical diagnosis, such as diabetic model, a reasonable model extraction attack should care about high accuracy for detecting both presence and the absence of a disease in order to achieve a valuable, usable surrogate model. So that's all I talk. I try to explain the attacker's point of view and revisit the adversary model a couple of times. And now Sebastian will talk about the detection part. Sebastian.
So Sebastian, go ahead.
Thanks, Buse. So as Buse and Asokan already mentioned, the adversary is leveraging public data, and part of the adversary model is for the adversary to be unaware of the purpose of the model. So some kind of behavior that you can expect is, for instance, to query images of cars to a bird classification dataset, or traffic signs to a retina pathy-based model. Next slide, please. And we can try to use this behavior to dictate these adversarial queries. So in our defense, we decided to create a binary pre-classifier for the API. And we call it a 1.5 classifier because essentially we're trying not to classify the queries into two distinct classes, but more so whether this fits the purpose of the model or whether it doesn't. So in other words, whether the images come from the same distribution as the victim's training set or not. And then if they don't, we would like to maybe fuzzy the prediction to give a wrong result and give the good result only to the legitimate queries. And this is something that you can see in the flowchart on the right. You'd get the query, run it through the binary preclassifier. If it's a legit prediction, if it's a legit query, we would give a valid prediction. If it's not, we would perturb it so that it maybe deteriorates the quality of adversary's model. And that's essentially it. Next slide, please. And shortly, how we did this, we took pre-trained ResNet models, and then we fine-tuned the very last layer by replacing it with logistic regression model to detect in and out of distribution queries. And very briefly, our method achieves high true positive rate and true negative rate on all data sets that were used in Knockoff, but Caltech. And the issue with Caltech is that it's exactly the very same data set, you could say, as ImageNet and Open Images. Obviously, it's not the same images. However, it's also a very general purpose data set that contains images of various classes, much like ImageNet and Open Images. And for virtually all other data sets, our technique has over 90% accuracy, true positive, true negative rate. While for Caltech, it's essentially 50-50, so it's a coin toss. And also notably, well, our method performs better than state-of-the-art out-of-distribution methods such as Odin and Mahal used for other purposes in machine learning. Next slide, please. And how we can summarize it is that, well, the larger the overlap between attacker transfer set and the victim's training data, the less effective the detection. And you could say essentially that if the adversary has exactly the same data as the victim, same domain, that is, he's behaving like a legitimate benign user. So if we consider a more realistic adversary, well, they do have access to more unlimited data from public databases, search engines, like Buse highlighted. They do have some knowledge about the prediction API, so they know to query birds to a birds model or cars to a cars model, and thus they can evade detection mechanisms identifying out through distribution queries, because like I said, they would behave just like a benign user. Next slide, please. So with that in mind, can we actually do something to prevent that kind of strong adversary? So for stateful analysis, well, there are Sybil attacks. The attacker can distribute the queries among many clients. If we decide to charge customers upfront to have some kind of cover costs, well, then we reduce utility for benign users that are not power users. And at the same time, if we restrict the access of the API, then we also are hurting users that would like to use our service in a benign fashion. Well, while it is possible, though, to slow down the attacker, and there are many papers related to this, this is exactly what I said. It just slows down the attacker and doesn't ultimately stop the adversary from ultimately stealing the model. And having said that, off to Asokan. Thanks.
Thanks, Sebastian. So, so far we were talking about image classification models, but the model extraction as a problem is not limited to image classification alone. So in the last year or so, there have been a number of other papers that show how other types of models can be stolen. So one of the notable ones is natural language processing models, and these use this so-called transformer models, which are again starting from a pre-trained model. And there is a paper that shows that essentially like a knockoff-like attack on transformer models can be stolen. A more interesting paper that also addressing natural language processing showed that you could actually even extract Google Translate, not for the necessarily for the purpose of sort of equivalent functionality, but for the purpose of finding the so-called adversarial examples. So as you may have heard, adversarial examples are specially crafted inputs that force a classifier to misclassify or mispredict what it would have otherwise done. And it turns out that many of these adversarial examples are transferable, meaning that if you can find an adversarial example against one model on the same type of data, then it's also likely to be an adversarial example against other models. So what these guys do, which is in a paper that's presented in fact this month, is they steal Google Translate with the purpose of finding an adversarial example, and then they show that the same adversarial example can also fool Google Translate. And I checked just before this talk that this adversarial example is still valid. It's an adversarial example. Maybe you can stare at it for 5 seconds to see whether you spot the adversarial example. So remember that adversarial example are specially crafted inputs that make the model lead the model to the incorrect conclusion. And you see that just because you change 100 degrees Fahrenheit to 102 degrees Fahrenheit, the model does something completely crazy and ends up with the wrong result. So this is still active. So that's for models dealing with natural language processing. There are also reinforcement learning models, which are not classifier models, but learn, sort of train themselves by given some kind of reward scheme where their actions based on observations of the environment lead to some rewards. Like these are used in sort of agents that play games, or agents that are inside robots, or in autonomous driving, and so on. So these are more difficult to than other models because they are less observable. You can only observe the action of the agent. The agent doesn't give you a nice complete prediction vector as such. So there's a paper that shows that you can also steal reinforcement learning model, again with the same sort of goal. You steal a model, find an adversarial example that fools the stolen model, and then try that against the original model, which ends up fooling the original model as well. Something that Sebastian has been doing recently is style transfer models. So style transfer models, you may have heard come across things like FaceApp, where you give an image, and instead of classifying the image, the style transfer model sort of transforms the image to another style. So you can make a person look older or younger, or change the gender, or given a photo, it can generate paintings in the style of some master, like a Monet painting. And essentially these models work these models are trained by having lots of unstyled images, but a secret source of a particular type of style. So for example, for training models to draw paintings in the style of Monet, you have to have some original Monet paintings. And then you let the model train using these these source styles, and come up with a model that, given a photo, can generate a painting that looks like a Monet painting. And now, exposed with a model like that, an adversary can just use a bunch of unstyled images without having access to any secret style images, and steal a model that does the same kind of functionality. So I'm not going to explain this further, but I'll just show you, give a flavor of what the results look like. So this is the original unstyled photos. This is what the victim model produces, like in sort of Monet style images. And this is what Sebastian's stolen model produces. So by this time, I hope I have sort of convinced you, or we hope we have convinced you, that model confidentiality is important because it constitutes business value. And if you can't ensure model confidentiality, then the incentive for people to spend lots of resources to train images for various problems might go away. But I hope we have also convinced you that models can be extracted via their prediction API. And even though we have sort of defense mechanisms that make specific assumptions and can be shown to be effective against sort of mechanisms like knockoff, when those assumptions hold, a powerful but yet realistic adversary can extract complex real-life models, and it's detecting such an adversary seems to be difficult, if not impossible. And the essential reason for this is that all of these detection mechanisms try to distinguish between queries that come from a genuine, honest user, and queries that come from a malicious user who's trying to steal the model. And for a powerful adversary with lots of data drawn from the same model as the same domain as what the model is built for, and who knows the structure of the model, their queries can be indistinguishable from genuine victim queries. So given that we can't really detect or prevent model extraction, what can be done to counter model extraction? So I'll briefly tell about one direction that people have been working on and that we have been working on as well. And essentially this is watermarking. So watermarking you might be familiar with in terms of media, like images or videos and so on, where you embed some information in the media in such a way that the adversary can't remove that embedded information without actually destroying the utility of the media. So you can't remove the image watermark. You can try compressing or doing all kinds of filtering techniques, but the resulting image will not be as good. And there have been previous works that show how to do watermarking of neural networks. And the basic idea is that you embed a watermark during model training. And these watermarks are chosen as sort of specially crafted samples, which typically are distinct from the domain of the actual training data, so that it doesn't affect the accuracy of the model itself. But because these models neural networks sort of tend to memorize training data, it will remember these specially crafted models. So that if you find a model out in the open that's being abused in some way, and you think that is your model, you can demonstrate your ownership by using these specially chosen watermark samples, run them as queries against this publicly exposed stolen model, and show, and you'll be able to predict what the outcomes would be. So you can convince the judge that this model is a variant of your model because you can come up with a set of watermark samples. And as you can imagine, any watermarking scheme should have a good enough level of false positives and false negatives, so it should be able to detect all stolen models, but it shouldn't be possible to frame some innocent model owner as having stolen your model. So these things exist. They only protect against the white box theft of a model, right? So in our case, model extraction, the stolen model is trained by the attacker themselves. So the attackers sort of choose how to query a victim model, and based on the result, they will train their own model. So they wouldn't oblige you by sort of, they wouldn't allow you to give a specially chosen set of watermarks and embed them in their training. So essentially what you have to do is to try to do the watermarking at the prediction API itself. So this is something that's in our current work, which is, you can find a version of that in arXiv. What Buse and Sebastian and other colleagues did is to try to embed the watermark at the prediction API itself. So again, if you are interested, we can go into details during the Q&A. So let me sort of summarize what we have said so far. So again, I hope you would agree that model confidentiality is important, but model can be extracted. And protecting model data with cryptography or hardware security, these are of course all useful, but they only protect white box model theft, against white box model theft. Once an API is exposed for potential customers, and without exposing such an API, the model is essentially useless. Cryptography or hardware security is not going to help against model extraction via these APIs. And based on sort of our analysis, it turns out that while you can detect model extraction in specific circumstances, if you assume a limited adversary, in general, it seems to be hard, if not impossible task. And watermarking as a deterrent is potentially useful. I think jury is still out whether it can be effective, but it's an avenue that should be explored. If you are interested in, so like I said, we have been working not only on model extraction, but other aspects of security and privacy of machine learning as well. And this is because, as we all know, machine learning is going to, or is essentially pervading all aspects of life, and therefore it's going to attract adversaries. And being able to understand the sort of degree of robustness of machine learning in terms of security and privacy is not only an interesting research topic, but also a very important one, because it's going to affect all of us. And it seems like industry is sort of waking up to this, and there is more and more attention paid to the security and privacy of machine learning, not only using machine learning for various security privacy applications, but security and privacy of machine learning-based systems themselves. There are also many other aspects that are not necessarily security and privacy, like fairness and so on. We are not particularly working on that, but we have a number of other aspects of security and privacy of machine learning, as well as applying machine learning for security and privacy problems. And if you're interested, ask us questions or check out this URL. So at this point, Zoom doesn't let me check Q&A, but if you have questions, you can ask in Q&A, I believe.
Yeah, thank you very much, Asokan. And now the floor is open for questions to our three speakers. I'm not sure how we do this. You can either raise your hand or you can write to the chat. And I think there's even a Q&A tab. So just
yeah, you can write it in the chat or in the Q&A, and the Q&A only comes out when someone is asking something, I guess.
I see. Okay, maybe I start with the first question so that we kind of kick off the Q&A session. Regarding the extraction attacks that you have shown, have you seen anything in the wild, like in practical deployments, where extraction attacks have already happened, or where companies already tried to do some defense techniques as you have proposed in a similar way, maybe? So is industry aware of these attacks?
So industry is certainly aware. So I, like I told you earlier this morning, I saw that there was a Gartner report that said that in the future, there's this big danger that a big part of attacks against systems are going to be attacks against machine learning systems, because machine learning is increasingly part of that. I don't know of any sort of attack against machine learning systems for real by sort of the black hat bad guys. Mm-hmm. But attacks against realistic systems have showed up. So I gave you an example of attack against Google Translate, right. And there have been others as well. Mm-hmm. I think another measure of industry being aware of this is to the extent to which industry is supporting this kind of research, right? So mm-hmm. every major company, the Google, Microsoft, Intel, they not only have their support academic research, but they also have internal activities. So IBM, for example, has like a toolkit that's meant for robust machine learning primitives, robust against this kind of attacks. And pretty much every major company is active in this. Mm-hmm. I think the reason why we probably haven't seen real attacks is because there's other low-hanging fruit that can still be okay. Another maybe useful thing to mention is that typically the machine learning models are not used as a sort of standalone service, right? Except in maybe rare circumstances like Google Translate. The machine learning model is part of a bigger system that may not be directly accessible to attackers. So for example, malware detection is like that. So they would, anti-malware companies use machine learning models, but they are one of several other mechanisms that are internal. So attacking them is also raises the bar. But of course, we know that eventually those bars will be breached, right, when there is sufficient motivation.
Yeah, I think so too. It's very important to analyze these aspects and raise awareness before attacks happen. We have seen this in many domains in security, especially in the area where we have been collaborating in return-oriented programming, where a number of papers appeared showing this attack technique, but there was no exploit in the wild really using that. And then it started with Stuxnet and all the browser exploits.
And so now I think every attacker knows about these techniques and has a toolbox.
I can also give an example. In the original knockoff attack paper, they tried to steal a face recognition API, a real world commercial API, and they test the accuracy of both victim and knockoff model using like face recognition data set, and they had a pretty good performance recovery. So I think this is a real threat for commercial APIs.
Yeah. Okay, I'm checking whether we have more questions. Please write to the chat or raise your hand. I can give you another question in the meantime. Regarding the watermarking scheme, the existing schemes that you presented, they were all focused on, for instance, if you sue a case and then you prove your ownership, right? After the fact, the work that you referred to as currently in submission, is this something which is more at preventing the attack and not detecting after the fact?
Not quite. So I think watermarking schemes in general address this issue that you can't prevent the attack, you can't even detect the attack taking place, but let's try to reduce the incentive for the attack, because if they try to use the model in some way, we'll be able to prove that it's a stolen model, right? So it's a deterrence mechanism. The difference between prior work and our work is that prior work is meant for these cases where I train a model, then I sell it to you, or I rent it to you. You then turn around, because you have now access to the actual model itself, right? You turn around and undercut me by reselling that service. And I find that you have set up a cloud service where you offer a translation service, and I'm Google, and I sort of rented my Google Translate model. So existing watermarking schemes are meant to prevent against this case where you stole the plain text model, the white box model. Whereas model extraction is a case where you don't even have access to the white box model. I don't give you access to the white box model. I give you an API. You query this API, and then you train your own model. And existing watermarking schemes don't apply to this case because I can't choose these carefully selected watermarks and embed them during training, because you are doing the training. So this makes the problem harder. And essentially what we do is when you ask queries, we are going to give you wrong answers to some of these queries, and these queries will serve as the watermark, but we can't do that with impunity, right? Because if we give too many wrong answers, then your utility would be bad. And we don't also have the freedom to choose which queries are going to be watermarked. If I'm training my model, I can choose queries that are far away from my, like the normal manifold of data, and choose them in such a way that it's not going to affect the quality of the model. Now you, as an attacker, is going to ask me queries, and I'm forced to watermark a subset of them. So these are the challenges in designing a scheme like that. But both ours and previous watermarking schemes are all such that you hope that, so if somebody steals the model and then use it internally without ever telling anybody about it, these methods are not going to help. This is like you choosing stealing my painting and then keep it in your basement. But if you try to publicly use it, if you try to exhibit my painting, or if you try to use my model to provide a service, then I will be able to establish ownership. That's the idea behind watermarking in general.
I see. Okay, we have the first question in the Q&A tab. I'm not sure if you are seeing that. Otherwise, I just repeat what is written here.
Yeah,
Does blinding the results of the prediction API model help at all for making extraction of the model harder? So for instance, multiplying or adding, subtracting random values to the result vector.
So I'll briefly answer, and then maybe Sebastian, you can take a shot. So this is sort of similar to what we do in this this Dawn, the paper that I mentioned here towards the end. We don't necessarily blind, but we give randomly flip the answer. We give a wrong answer to a small subset of queries, and those serve as the watermark. So these come with the constraints that we don't get to choose what those queries are, so we can't do that extensively, and we have to make sure that the watermark queries cannot be detected, are indistinguishable by the attacker, right? So the attacker is asking some questions, we are giving them answers. They shouldn't know which questions are the ones where we flip the answer. Sebastian, do you want to?
Yeah, so maybe to add a little bit to this, by modifying this prediction, you can embed the watermark, like by our design, what Asokan just explained. But also something that Buse mentioned earlier and was part of proper like defenses is that, yeah, like you suggested in your question, if you do some kind of abstraction, if you like clip, or like Buse said, and give the top label, it's going to make the model extraction harder. But as we mentioned during the conclusion, this is just that. It makes it harder, but it doesn't make it impossible. And you can offset this difficulty and accommodate for it by just using way more data. And if we consider an adversary that is, well, within a sensible adversary model, this is not completely impossible. Like, this is a sensible assumption. And I see that there is another question that I've read already, so maybe I can take it since I'm already speaking. So Hamid asked us if it is possible to steal a more complicated model such that, well, the usage of the data is not obvious, the type of data is not obvious, because we concentrate on the image domain. So yeah, in our work, we do concentrate on the image domain because usually you need this kind of, where you need complex models is for the image domain or for NLP or for GAN transfer. However, as Asokan mentioned at the beginning of the presentation, initial work on model extraction showed that you can steal simple models that work with this kind of categorical data, simple metrics, and malware detection is that kind of model, logistic regression, decision trees, and so on. I think, though, that why we mentioned malware detectors in this particular presentation is not necessarily about the kind of model or domain that you have, but rather the fact that malware detection is not just a classification model that exists and you interact with it. So it's just a small block in a much bigger malware detection pipeline, right? There might be some code analysis tools. They may be literally 20,000 people in some countries sitting and looking at the binaries. Like, this sounds stupid, but well, it is something that is possible. There might be metrics that you're completely not aware of. So by trying to steal that kind of model, you don't even know what to send because you don't know what the company is actually having and looking at. So interacting with the model on its own might not be possible. And I think this is the big problem here, where you have this big black box system where machine learning is just a subset of it. And then it gives us a completely different level of difficulty, a different scale. Yeah.
So there have been models that are non-image based that have been stolen, like machine translation and so on. In the case of malware, like Sebastian said, I think malware companies are not maybe particularly worried about model stealing for these reasons. What I have heard from malware companies is that they are more worried about poisoning, that somebody would sort of manipulate the for example, online training data that malware models use, not necessarily with the intent of sort of evading on the spot, but rather degrade the quality of the model down the line. Again, I think they are less worried about model stealing because their models are part of a bigger system, and in a way they are sort of relying on this obscurity aspect. And we all know that relying on obscurities may not be so sort of so solid down the line, right? But they are worried about other aspects of adversarial behavior, such as poisoning.
So So it seems that we don't have any more questions.
I can maybe put some advertisement here that I don't know
Yeah,
if there
of
are
course.
potential students, but we always look for people to come and work with us. So we currently have a open position for somebody, a postdoc, to work on machine learning security and privacy, but we do work on other system security aspects as well, like the kinds of things that Luca mentioned, like runtime security and so on. So if you're a system security person, even if you're not working on machine learning security and privacy, we'll love to hear from you if you want to come work in Canada for a while.
Okay, it seems there's nothing else to be discussed at this moment. So I take the opportunity to thank you again for giving this very nice talk. Even for non-experts in machine learning, it was very understandable. I learned a lot in this 1 hour. It was great to see you here. I think it's tough times for all of us because we cannot travel, we cannot see each other on conferences. So it's good to have this opportunity to meet virtually. And with that, I think I will conclude this distinguished lecture and hope to see you soon again. And if you want to get in contact with Asokan, just write him. He's available on many channels. He has also a very good Twitter account, which I personally check from time to time. Yeah.
Thank you, Luca. Thanks for inviting us. And I think in particular, on behalf of my students, it's very valuable for them to have a chance like this to give talks.
Yeah, sure. You're welcome. Thank you so much.